Let's now talk about the space loss. Let's look on the antenna here in the drawing and assume it radiates an energy in all directions, omnidirectional or isotropic antenna. Let's assume it radiates it equally towards all directions. Then what do we see here? If we take the energy at, let's say we freeze the time after 1 second, and the energy spreads away from the antenna, then we will get a ball of a certain size in which all the energy is located inside. Then we will let the energy propagate further and we'll stop their time again in after 2 seconds. Then of course the sphere of energy that radiates from the antenna was increased 2 times. Okay, and now, but the same power that was captured in the small sphere in the 1 second freeze is the same energy that is captured in the 2 seconds sphere. So in this case we understand that since the ball is the sphere is getting bigger and bigger, then the power density on its surface has to get lower and lower as we get away from the antenna. For a small sphere, the area of the surface of the sphere, of the imaginary sphere around the antenna, is small. As we get away from the antenna, the surface of the sphere becomes much bigger, and then the energy has to spread upon all the surface. Then the power density becomes lower and lower as we get away from the antenna. Okay, here there is something I want to emphasize. Antennas, okay, we measure distance in meters, but antennas doesn't really care much about meters, okay? Because antennas has different frequencies. The units that antennas are interested in is wavelength. So everything I measure in wavelengths. The distance I measure in wavelengths. The area of the sphere I also measure in wavelength square. That's why in this formula here we see R per lambda, which means the distance in wavelengths. Okay, the distance in we take the radius in meters, we divide it by lambda, and then we get the distance in wavelengths. And what is actually 4 pi distance in wavelengths? This is actually the area of the sphere. The area of the sphere increases as we get away from the antenna. And the power stays the same. This is the same power that we injected to the antenna. So if we take this same power and we divide it to an increasing area, then we will get a reduction in the power density. And the power density is the loss that we will have as the energy propagates away. So if we look, this is the formula that represents this. We will look at it. This is 20 log 4 pi multiplied by R, that represents the range, divided by wavelength. And this actually represents how much the energy fades in case we have a vacuum volume between the antenna and the point that interests us.